Hello everyone, my name is Juliana. I'm a PhD student at CNAM, and this work entitled Self-supervised learning with auxiliary metadata for Earth observation was part of my master's thesis that I completed while I was a student at the University Paris Dauphine and an intern at CNAM. My main supervisors were Arnaud Brelat and Javiera Castillo from the Cédric Laboratoire, and today I come to present it to you. First, as everybody already said, in satellite images and Earth observation images, you have a lot of images, but not a lot of labels, because labeling is work that requires a lot of time and also domain expertise. So self-supervised learning is a very good approach to work with satellite data, because it allows us to learn powerful visual representations without any human labeling. But there's still a gap, because self-supervised learning just uses the images and ignores the metadata that is captured along with the image. And we could use this metadata to improve the performance. So we have two main research questions, which is, can metadata improve the performance, and how we can introduce this metadata into the training pipeline of a self-supervised learning model. First, I would like to recall the concept of contrastive learning. It's basically a methodology where you have basically two augmentations of an image, and you try to train a network to basically push together the two representations, two augmentations that came from the same image, as you can see in the left. And in the right, we try to repel the two versions that comes from different images. And contrastive learning has demonstrated a strong performance, almost matching supervised settings. And within the contrastive learning framework, we have the concept of self-supervised learning, which is basically a methodology, a paradigm that you can use to learn representations from the data without having to count on labels. You have the pretext task, where the goal is basically to make the neural network to learn important features from a set of images by solving a task such as, for instance, predicting the rotation of an image or predicting the missing parts. And based on this knowledge that this neural network achieved, you can transfer this knowledge to a downstream task that usually involves labels such as segmentation or classification. And it has already demonstrated that it can learn robust features that are very transferred to those downstream tasks. And SimClear is a very popular framework within the self-supervised learning, which consists basically in taking an endpoint image and creating two augmented views from it by basically doing some editing of the images, such as random crop or color jitter. And the goal is to put those augmentations that comes from the same image together, while pushing the negative ones that comes from different images apart. This more technically is translated into this architecture, where you basically have this, I don't know how to use this input image X, where you basically created two augmentation views here, V1 and V2, and then you pass this through a shared encoder, producing representations H1 and H2, and next use a projection head, such as an MLP, to get those projections. And the goal is to maximize the agreement between those two projections by doing, for instance, the cosine similarity between them. And usually after pre-training, this projection head is discarded, and we keep just the encoder to do the part of transfer learning and downstream tasks. But as I said, SimClear has a limitation, because it treats all the negative images as equally different. For instance, if you have two images that comes from almost the same place, like they are not very different, even though if they are from the same class, simply would treat them as different as another one from a different class that is far away. So our goal is how we can make those two images that are not very distant of each other and are from the same classes, how we can treat them as more positive and not as negative as the one that is far away and from another class. Well, we got inspiration on a previous work by Dufumier et al. Made in 2021, which is called the wire loss, that where they claim that not all negative images are equal, and the goal is to use the metadata that comes with an image, such as the location, the timestamp, or the ground sampling distance, into the traditional contrastive loss. Their idea was basically to work with brain scans of patients, where basically they wanted to say if a patient has Alzheimer or not. And for this, they used a metadata that they had, which were the age of the patients. So they expected that patients with similar age would have the same diagnosis of a disease. So their idea is that images with similar metadata should be closed in the latent space, rather than one that has a different metadata as this one. So they proposed this wire contrastive learning, which I will describe in the next slide more technically. First, they assumed that they had an unlabeled data set consisting of an image P and a metadata N, and also that they have the representation similarity score, F theta, between two views, V1 and V2, in the embedding space. And just to give you a bit more context, this is the traditional noise contrastive estimation, inference loss, which is used in contrastive learning, where basically the goal is given an income image, its goal is to find the other positive among all the other negatives in the batch. And instead of just doing this hard assignment, they introduce this red term here, which acts like a soft labeling, where you can push together images that share similar metadata. And here, in this red part, we have a W of a sigma described here, which is the radial basis function with a kernel parameter theta, which allows us to, giving the metadata y here, we take the distance between them and use it as a weight to try to approximate metadata images that have a similar metadata into the latent space. But our methodology is not is actually with medical brain scans, is with satellite images. So we decided to work with the Eurostat dataset, which some people already presented to you. And we decided to use metadata. There are a lot of metadata available, such as the location, red sampling distance, the timestamp, and etc. And we tried basically to fuse satellite images and metadata by contrastive learning. And we modified that term that we showed before to, instead of using this Euclidean distance here, which is not very appropriate for Earth because Earth is a sphere, we tried basically to use the Haferstein formula to compute the distance between those two images, metadata, which is given by this formula, and is based on the radius of Earth and also on the great circle distance of it. And our idea is very similar to our references. We decided to look just at the locations. So two images that have similar locations, they should be close together in the latent space, while one that is more far away, they should be also far away in the latent space. So it's not working. Sorry. So we adapted this, replacing this Euclidean distance to use the Haversine formula. And just to repeat a bit more, we use the Eurosat dataset, which is proposed in 2019, which has 27,000 of satellite images over European cities of 64 by 64 pixels. So it's a pretty small image, and that covers 10 different land use or land covers, such as classifying if a place is a forest, a river, an industrial building, a residential building, and these were extracted from as patches from a bigger image. And how we conducted our experiment, basically we pre-trained the Simply framework using a HisNet 18 as an encoder. And after pre-trained, we freezed the encoder's weight. And next, we evaluated it using a linear probing by fitting a logistic regression classifier on top of the frozen features. And after this, we compared our results. We called our loss a local error loss, to be similar to the wire error loss. Okay, sorry. To the random, supervised, and other versions of our wire. And our method has got the best accuracy among the others, almost matching the supervised settings. And yes, in other methods such as F1, precision, and how we also have the best score. Our confusion matrix was also very good. There was just some confusions between classes that are really similar. And those are our OMAP plots showing the organization, the space, which basically shows that we have a very organized space for the supervised setting and unorganized for the handle weights. And our is in the between. It's similar to the Simply, but it's more informed. And yeah, our contribution was to adapting the contested wire loss for satellite images. And we are right now trying to extend the results, pretending enlarged and more diverse data sets, and also doing transfer learning. And yes, we essentially improved our self-supervised baseline, but it still has a limitation, its scalability to compute all the distances. And we look forward to improve it. If you have any feedbacks, it will be very appreciated. Thank you.
Time for one more questions.
Question about the philosophy. So is like the spatial relation always like the best? For example, two images of city in the United States would really look alike, even if they are very far away. So what do you think in that case the cross matching?
In this case, we don't address this actually, because we just want to put images that are already similar, even more similar. But that is that is a part of the laws which accounts for the similarity between the images, but the weights itself they may not help because they are distant from each other. So I think this part will be more handled by the image after the loss. Yes.
Questions? So let's again, Juliana.